Okay.
It's working?
Yeah, it's up. You're not on the first slide, though.
Alright, nice.
Yeah.
So, yeah.
We can start
So
with
I
the
will
first slide.
basically
Yeah.
run it in order of like this.
Okay.
Alright. So I am a rising junior at Pitt with computer science major, neuroscience minor, and also a math minor. So I am interested in neural computation, artificial intelligence, cognition, and data analysis, all of which are kind of interdisciplinary. So the goal of this project, so firstly, the emphasis of this project is development. And development can be long and can be short. And I choose a shorter one, which is synaptic plasticity. And specifically, that is association, and it is a real process happening in real nervous systems, especially in early childhood development. So the goal of my project is to simulate that sort of synaptic plasticity and to produce a proper visualization of this process. And the most obvious implication of this project is to help the understanding of early childhood development, because I will visualize important data and also the change of network structure and connections. And therefore, also it is very easy to see the development of the overall network. And I am able to investigate if the development of the network follows any patterns, and that sort of pattern might inspire neuroscientists. So, well, that sounds ambitious, but that might be possible. And also, I think it can help me to determine which features, like recurrence, like the number of layers, can contribute to self-assembly of the network. So, to begin with, I plan to model associative learning relating to senses. So to model this kind of plasticity, I take the idea of Hebbian theory, which is neurons that fire together wire together. So the network should have drastic changes in not only its synaptic weights, but also its connection patterns or structures. The drive for this development are two multidimensional senses, that is, two kinds of receptors with different sensation rules, and I will explain the rules in later slides. So also, since the stimulus sources are distributed in the space, the movements facilitates the neural development. And also by learning and learning, the Braitenberg vehicles start to have tendencies towards stimuli. Maybe it can go towards the stimuli because it's like it, or go away from stimuli because it doesn't like it. So therefore, movement manifests the neural development. But movement is not a primary effector, and I will talk about the primary effector later in the slides. So synaptic plasticity happens among the interneurons in the network. So basically, synaptic weights are updated using generalized Hebbian algorithm, and the equation here is shown. But the equation here is for just updating the weights between two layers. So basically, GHA is updating the weights according to the association between the inputs and outputs, and commonly it assumes that there is no self-connection, as you can see in the second line in the equation. But self-connection might be important in some way, but now it is currently not clear. So I might start my implementation without self-connection, and then try to add self-connection reasonably and to see if it can create any effect. And recurrence. The important recurrence is very important, and it can be like classical to across one layer, but it can also across multiple layers. And the network size is self-reducing. That is, the network starts with a lot of neurons, a lot of random connections, and through the visualization, we should see that the size of the network should reduce by itself throughout the self-assembly process. So since it is Braitenberg vehicle, it contains receptors, effectors, and innate connections. So there are two kinds of receptors, I said. I call them olfactory system and gustatory system, but they can actually be any other kinds of sensations in real life. So it's just like an abstraction. The olfactory system receives inputs as the values of stimulus sources applied to an exponential radial basis function. That is, in short, that is like the values of a stimulus source decay with distance exponentially. And the gustatory system receives inputs as the values of the stimulus sources applied to a Heaviside function. That is, only when the Braitenberg vehicle is within a distance range from the stimulus source, it can have taste. And also the gustatory system yields feedback, that is a degree of like or dislike. And the feedback will affect the movement and also affect the learning. So it's not, maybe I can do this. It's working right now? All right. So I made an animation of the receptor. So as you can see, as the particle, the agents move along diagonal, when it is very close to a stimulus point, it have taste. Otherwise, it doesn't have one, right? So also, as I said, there are two kinds of effector. The primary effector is the change of connections in interneurons, and I will visualize it with network X. And the secondary effector is the movement. That is, the Braitenberg vehicle start to have feelings based only on olfactory stimuli and move based on those feelings. So it is like, firstly, it can have feelings based on the gustatory stimuli, but now it can have association with the gustatory attributes with the olfactory attributes, and therefore when it has olfactory stimuli from a very large distance from the stimulus source, it can have some sort of feeling and move based on those feelings. And also, if just letting the Braitenberg vehicle to move randomly, it's going to be less efficient. So I introduced curiosity. So it is basically that the Braitenberg vehicle tend to go towards nearby sources, stimulus sources, and that can be implemented with a KD tree, which is very commonly used in finding the case nearest neighbor. And it is a tree data structure to store the space partitioning information. So as you can see in the left side of the slide. So it is an example of KD tree. It separated space based on X median, Y median, and alternatively. So on the right side is the part of code that I make the searching method not exact, because this project doesn't necessarily need to find the nearest neighbor. It just needs to find a nearby neighbor. And in some corner cases, finding the nearest neighbor is costs a lot of time, especially when some stimuli are clustered together. So I make the part of the code that to not find the shortest distance to the nearby boxes, and therefore not going to too many subtrees, and therefore save some time. So I tested it, and with thousands of stimuli, and time saving is significant. Interconnection is also very important because it is simulating the nervous system. So the interconnection represents natural rules encoded in genes, and it is among primary receptor neurons and primary interneurons. And the basic function is to lift the problem to a higher dimension. So for connections to be innate, it cannot be eliminated by the plasticity or by the stimuli, and I will design it. And only me can eliminate the connections. And also the innate connections are much less subject to plasticity. So I will implement the network in Python 3, and if the speed really cause a problem, then I will translate them into Python, and I don't think it's not going to be a large amount of work. And the visualization is through Matplotlib and NetworkX. Two of them are very nice Python library to visualize data and also the graph, the network. And documentation will be through Jupyter Notebook because it is designed for Python, right? And storing network structures is through Python binary files or XML. Because in some scenarios, I don't need to start with a new Braitenberg vehicle and do the simulation again. So probably I need to store the progress and then revise something and continue the simulation. The timeline, so testing the network is a little bit tricky, so I will break the coding parts into 3, and between the coding parts will be testing and visualizations. So in the first period, I will finalize the codes of the init parts of the network and build a stimulus and environment class, and also do some immature visualization of the data and of the network, and also test the init parts not just in schema but also in the whole init system to see if it works. And then I will do the construction of the internal connections and Hebbian plasticity, and also make a mature visualization panel and to test the neural development with visualization. So till then, I should at least produce some mature animation of the network, the change of the network and development. And finally, I will finish the feedback circuit that controls the movement and do the visualization and progress storing functionality. Finally, I will finalize the work and improve simulation efficiency by improving data structures, algorithms, or using Python, as I said, and then I'll do documentation and detailed performance assessment. There will be 2 buffer weeks for unpredictable delay and any potential additional work and optimization, etc. So if time allows, I actually have a lot of ideas to be implemented. So here are the 4s. So firstly is the stereotype, or say prior drive. And the term prior drive is from Dr. David Heger's theory of quarter function. And I won't explain prior drive into details, but basically prior drive bias the activities of neurons and consolidate synapses. And it can also cause oscillation, and that is the key part, to cause oscillation in the neurons if there exists any multistability. So that means I will introduce a competition between the stereotypes and neural experience if time allows. And that I think is very interesting and make the model more realistic. And the second idea is to introduce secondary association. So for example, what if good stimuli are always distributed on the right side? So previously I was talking about the primary association, that is associating feelings produced by the taste with the smell. Now it is associating the smell with the space information. And the third one is to increase network depth and recurrence complexity and to compare the contribution to learning efficiency and results. And that was an idea from a paper that I read that saying that there might be some sort of functional equivalency between the network depth and recurrence complexity. So maybe I can do some little experiments, little informal experiments and to compare them and to see if I can draw any sort of conclusion. The fourth idea is to add one more sense. So it simply adds some difficulties, but it is a fun thing to do. That's it. So any questions or suggestions?
Thank you, Ziyi. Sorry about the technical difficulties, but that's the way these things go. So I thought that's a very interesting approach. I think there's a lot there. So, I mean, I get the sense that you're going to model two different sensory inputs into a vehicle, and it's a developmental model. So you have a focus on plasticity and a focus on Hebbian type processes.
Right.
Is it? I mean, do you see this like being? Are you trying to refine this down to like? Are you trying to refine this down, or is this like? Are all these elements going to be included in the final model? What's your approach?
So do you mean what's in the final model?
Yeah, so like when you expect to have to like make decisions about what to include in the final model, like as you're working through it and getting things to work, do you expect some things to fall by the wayside?
Mm-hmm. So yeah, basically, my idea is to make them all up from scratch. So, is that answer your question?
Kind of. I mean, yeah. So as you're doing it from scratch, there are going to be things that work, things that don't work. Do you anticipate any sort of like difficulties with like getting things to work, or maybe you have to take a slightly different approach, or have you tested these things out at least a little bit, or what's your?
So basically, actually, adapting to stimuli like as I said, the taste, to have feelings, to a degree of like or dislike, and that will affect movement. This part is going to be pretty easy, and I think actually Symbrand has the Java version of those parts, so I think there will be no problem with that part. But for the synaptic plasticity, I'm actually not really sure about that, because I think there is no like instructions or theories about how to design the structure of neural network, right?
Yeah.
So yeah, it is like to try different models and to try to fit it in and to see the performance, right?
Right.
So yeah, I'm pretty not sure if my design is going to be working or not.
Well, yeah, that's why we do. That's why we do science. We have to figure out if it's going to work. But yeah, it'll be fun. I think it'll be an interesting to see what actually works and what to actually evaluate different outcomes. Like you'd have a series at the end. You might have a series of different results depending on how you set up the model or depending on the inputs. And so it'd be interesting to go through those and see what they look like. So, Stefan, do you have any comments?
Yeah, I do have, and it was really interesting for me, like the part where you said that this development would be kind of modeling development or brain development of children, if I understood it quite right.
Yeah.
So, I mean, is it like what's do we hypothesize on that, or is it have there been some research in this direction that some gustatory or olfactory stimuli do develop human brains? I just don't know. It would be really nice to know the background of this claim.
So well, as I learned in my neuroscience course, in the brain of an infant, there are a lot of connections and a lot of excitatory connections. And throughout the early childhood development, a lot of connections will be eliminated, and also there will be a lot of neurons to be eliminated. So that's why I said here the network should self-reduce in its size, right? And also the ratio of the excitatory and inhibitory synapses will change. There will be more and more inhibitory synapses. Is that answer your question?
Yeah, I guess it does. And I have also then I have a little bit of input for you. It's just that's a great thing called Fermat library, and as you said about removing synapses with the time, I remember just a nice paper that had been sent there. It was called The Function of Dream Sleep, where the scientists claim or maybe hypothesize on that during sleep some neurons can, or some connections between neurons in humans' brain can be removed, and that's why that's why we see some dreams that are not real, because kind of our brain kind of tries to recombine things that are not really exist, and then like these connections will be removed. So I mean, just you know about this paper, right? Yeah.
A little bit, yeah.
A little bit. Yeah, I can just send you if you want. It was quite an interesting read.
Oh, sure. Thanks.
So yeah, it's just, I mean, it suits the topic, right? Yeah. So if you want, I can just send you the link afterwards.
Okay. Thanks.
Well, thank you, Ziyi.